So that LVI null thing is pretty bad. I deployed the patches on the test system. The overhead is just horrible, but I won't need it anymore anyway.
But I mean, at least it's not as bad as all those physical side channels that we've seen. They were really bad.
Yeah. Anyway, I'm done. See you around or at the graduation ceremony.
Okay.
Side channels are everywhere, most of the time we're unaware, but horses know we're leaking all the time. When looking in the fridge, when coffin does the bit in bridge, your side channels for fun and for the prize, cause side channels are with us all the time.
Oh, this one here doesn't belong here. You know, the physical attacks, they were quite powerful.
Yeah, but they're unrealistic. You need physical access to perform them.
Yeah. But think about it. Even without a physical contact to the system, you were able to mount an attack with an EM probe. That was quite powerful. Or by connecting this to the power socket on the wall. Yeah. What are you doing there?
Oh, I'm scanning the file system to find some information leakage.
Okay. What kind of information leakage?
Any sort of something to break KSLR or something like that.
KSLR breaks, I mean, they are powerful, but power analysis attacks were able to basically leak any data, a secret key from barely any measurable.
Noisy. Noise? What do you mean?
Noise can be a challenging obstacle when performing side-channel attacks. The noise is usually statistically independent of the secret, which enables eliminating the noise with statistical measures like averaging. The noise converges, in our example, towards zero. With a sufficient number of samples, an almost noise-free average trace can be obtained.
Power difference.
Yeah, there was also this differential power analysis. This is quite powerful. Look at this. I found this Intel RAPL thing.
What am I seeing?
You see the power consumption of my laptop.
What did you say was this interface called?
It's called RAPL, so running average power limit.
Can you just access this as an unprivileged user?
Back when we started working on Platypus, the interface was actually completely unprivileged, so you did not require sudo to access it.
So it was open for everyone to read.
Yeah.
And maybe also here, what if they don't have the patches?
So well, you can see that I can read it.
Yeah, right. What can you do with that?
So if I now run stress in parallel with the power with the tool, and I monitor the energy consumption, I can see that it suddenly increased. So I'm currently consuming much more power than I did before. And if I abort the stress again, we can see the drop.
This is like software-based power side channel attacks. Wow.
Yeah, at least the channel is there. Let's check this out.
Okay. So, what did you want to show me?
Look at this. I have a histogram here which shows cache hit and cache miss, and they have different energy consumption.
Right.
Although distinguishing cache hits from cache misses sounds like a trivial side channel, this is sufficient to determine the location of the kernel in the virtual address space. Daniel and Andreas measure the CPU energy consumption while repeatedly accessing all possible locations. During access, the virtual and physical address mapping is resolved and cached in the TLB. However, the CPU cannot cache translations if there is none. Therefore, repeated accesses on empty slots require more energy. On the other hand, if we find the correct location, consecutive accesses reuse the cache translation and save energy. In the demo, we see an energy drop at the exact location of the kernel. Therefore, Daniel and Andreas can break this protection mechanism by observing the energy drop using the software-based power side channel.
Also, why would you do that? It's you could just use timing and you would...
Yeah. But there's more. Look at this. Here we see different instructions with different energy consumption. So I can now distinguish instructions based on the energy consumption.
Yeah. But
I know. Wait, there's more. So this also works within SGX. So if you look at this histogram, you can see again different instructions executed within SGX, and they still have different energy consumption.
Wait, what? Wait, you can distinguish what instructions were executed inside SGX?
Yes.
Based on the power consumption?
Yeah, but there's even more. I also have done this with different data. So if you look at this plot, where we use the IMUL instruction, so the signed multiplication instructions, we can also see different energy consumption based on one of the data operands used in the multiplication.
Whoa, different energy consumption for different data values? That's a problem, right?
And it also works for the shift instructions, as I show here in this histogram.
Wow. Is there, I mean, this is about power consumption. Is there any model that fits the power consumption difference?
I also looked at that. It took me weeks to generate all the data. Here it just popped out in seconds.
I mean, we could insert one of those fast-forward comedy scenes where weeks pass by and the beard grows.
No, it's fine, it's okay. I also looked at that. So here's the plot of the move B instruction. This instruction just loads a single byte from memory. And here we can see the energy consumption for different loaded bytes.
So you can see the Hamming weight of the value that someone reads with mov B?
Yes, and if you take a closer look at this trend here, we can see even more information.
That's the jackpot. You know, I've been waiting for a side channel like this for 29 episodes. But you can't say this, right? Such a long time. Now we finally discover this new side channel.
And I even tried it out on different machines. It basically works everywhere.
Does it work on Claudio's test system?
Yes.
On SGX? On the SGX enclave that he has?
Yeah, probably. Either we have to attack the RSA signature or the AES encryption.
Some months ago we worked on physical side channels, on RSA for instance, and there we had some trace with zeros and ones, and that was based on the higher or lower energy consumption. Could we do something like that?
Not really. RAPL is fast, but not that fast. So if you take a look at this table here, you can see that the fastest register
is just 50 microseconds.
Yeah.
That's much worse than with an oscilloscope. How long does one RSA exponent bit take?
Way less. But that actually depends on the length of the used modules. So if you have a longer and longer key, then the individual bits take more time.
Okay. So what then?
So you can even see activity from SGX.
Yeah, but it's super slow compared to code execution.
Yeah, and also the difference are quite small.
Yeah.
If we only had a way to repeat the measurement over and over again.
You mean the same instruction?
Yeah, to accumulate the energy consumption.
Wait, but like a few weeks ago, we managed to single step an enclave by either unmapping pages or by having interrupts, right?
Yeah.
But single step, we would need to zero step. Since if we single step, we simply jump over the instruction. And we would like to repeat it.
But we can. This was actually the case that annoyed us a few weeks back.
And you could probably also do something with a very short timer interrupt here. So I set up a timer interrupt for the CPU and then run the enclave again.
But how short should it be?
I don't know. I mean, let's start one cycle.
Then the enclave won't do anything.
Yeah. And then we increase it until it does something.
When the timer interrupt was too low and the enclave wasn't able to do a step.
Yeah.
Wait, so you can actually zero step? Let me try that. It's kind of crazy. With this SGX thread model, we can single and zero step a victim. This is usually not possible in any thread model.
Yeah, the thread model is really powerful. It's really ambitious, but because of that, it also has a lot of problems.
So Here are the results of single and zero stepping the bits of an RSA exponentiation.
Wow. Well, you can really see the ones and zeros there. That's interesting.
But then there's a difference in the instruction stream, different code executed, right? It's not really constant time code.
And?
If you report that to any vendor, they will just say this is not constant time code, so it's not relevant.
Yeah, but I could also attack ASNI with this. That worked with physical side channels with this differential power analysis.
Yeah. DPA attacks.
Yeah. But it's super tricky because an ASNI encryption with the ASNI instructions is usually a few cycles. But a RAPL measurement for a single sample is like a few thousand cycles, 100,000 cycles.
We could repeat the same ASNI encryption over and over and over again. For instance, if we are looking at disk encryption, this could work. And then we could fill an entire RAPL measurement window with all the same ASNI encryption.
It could work. We have only a small number of samples, but a lot of traces within these samples. So.
And that's a trick that worked with DPA in the end. For DPA, we had this prediction vector, and we moved the prediction vector over the measurement matrix, and at the right offset where the operation we targeted, where this happened, the last round, maybe the S-box lookup, where this was, there the correlation graph then had a huge spike, and we could really tell that we had the correct prediction.
Actually, this differential power analysis with the model is usually called in new literature correlation power analysis, because you correlate some measurement with the actual trace, with the predicted measurements.
But this time we only have a prediction vector, which is the Hamming weight of the last round, and a measurement vector with a single measurement. So there's nothing to move around here.
Yeah, but it should still work, because the operation we target is still inside the one measurement sample we have. And the Hamming weight of the prediction and the Hamming weight of the measurement, they are only correlated if our model or our prediction match.
Let us take a closer look at the proposed attack from Jonas, Daniel and Andreas. The target of the attack is an AES key securely stored on a computer, in our case, Claudio's test system. The computer exposes an interface where we can trigger message encryptions and record the energy consumption during the encryption. We store the encrypted message and the measured energy sample for later use. In contrast to our previous attacks, we only observe a single measurement per encrypted message. To recover the secret key, we require a model of the CPU's energy consumption. Furthermore, we use the structure of the AES keys and how the AES state is transformed during the rounds to break the key into smaller parts. These parts can be analyzed individually by using the recorded data and compute the hypothetical energy consumption for each of the possible values of a key part. We now search for the hypothesis that correlates the most with our recorded data. This hypothesis corresponds to the correct key part value. Finally, we simply repeat this process for the remaining key parts. However, Jonas, Daniel and Andreas first need to figure out which energy model to use in the attack. For example, we can use the Hamming weight of a state after an AES round. Another common model would be the Hamming distance between AES states of consecutive rounds. Therefore, they first need to analyze which model is the best to use in our attack.
So with a known key, I've recorded a few million samples for different inputs. And I've computed the Hamming weight of each of the states.
And
I've also recorded the Hamming distance between those states.
Okay.
So
and what did you find?
The Hamming weight of input and output leak, especially here and here.
That's not useful. We have input and output anyway.
Yeah.
Also the Hamming weight after the first XOR within the first round leaks. Much better. We see leakage in pretty much all the rounds.
Wow. But in the previous AES attacks that we mounted, we tried to focus on one of the last rounds so that the remaining search space is low.
So this is the last t-table lookup where these intermediate values are used.
Yeah, and we recover the 16 candidates for each of the intermediate inputs here. But if you want to compute this through, how would that work? The key is used here and we don't know the key.
But we know the ciphertext and we have 16 candidates for the intermediate value. So we use the same trick as before. We have this XOR and we can turn it around. So we can compute through here with these 16 values, and if the ciphertext fits, we know the key.
We now have to group them together by ciphertext, but it will be all scattered with many ciphertexts. Then you will have the same key candidates often, but only the correct key candidate in all the runs.
We can do that here as well. If we target the last round, we should be able to obtain the key. Wow, it works! Look at this! You can see here all the 16 bytes of the AES9 key completely recovered.
Wow. I think we should report this.
Maybe we should first search for something, if there's something
That's an idea, but yeah, then...
How do we search for that?
That's a good question. Let me try. Power analysis, attacks, maybe software.
Software DPA attacks?
No, what I find here is all physical attacks. Let me try software DPA. Software DPA. No, this is also all physical. Power, side channel, software. Oh no.
Don't you think that the joke is getting old?
I thought it's sort of like a running gag.
Yeah, but it would have to be funny for that first.
So this is called the platypus attack, and it's already mitigated?
Yeah, sort of. There are patches for this that make the interface less accurate or even unavailable.
But I don't think that that's the best solution for it.
Yeah, but I mean, the best solution or the better solution would be what we discussed some months ago, to use masked implementation.
More shares then?
N shares, 5, 6, 7 shares.
Yeah, we call this higher order masking.
But I mean, we can break all of that.
You can break all of that, but it will be more expensive.
But no one would do that in software.
Yeah, right. Not yet, but who knows what the future brings.
I think we should mention the frequency throttling side channel here.
Oh yeah, frequency throttling side channel. There are power consumption limits, and the processor has to adhere to those, and thereby they influence the processor's speed, frequency. And Platypus showed that the data values processed influence the power consumption, and therefore this also influences how close you get to those power consumption limits, and therefore the CPU frequency and speed.
Mm-hmm. Which means that processing different data values translates to different timings.
And then what? Then you can really only resort to masking?
So this platypus attack changes a lot. Now we have this whole range of physical attacks which become now available from a software attacker.
And long-term mitigations against these attacks will become necessary.